Wait for it. There we go. Right. Okay, so today's session is all about physics paper 1, the required practicals. So I think there's 4 for combined and then an extra one. I think something like that. Can't remember now. I've done this anyway, but I shouldn't really know how many practicals. So the first one is on specific heat capacity. So it's linked to how heat is moved, the energy topic, basically. Specific heat capacity, you need to know the definition of that. So it's energy needed to raise a material, whatever it is, by 1 degree, 1 kilogram of mass by 1 degree, basically. So you do need to know the definition. What's the point of this practical? It's to find out the specific heat capacity of that material. Okay. Oh yeah. There's different ways to do this. You can do a joule meter, or you can work with an ammeter, voltmeter, or power meter. There's different sort of setups to measure this. If you watch the required practical, I think they use an ammeter. Hang on, there we is. Hang on, I don't know that one. That's chemistry as well. Right, if I don't get to it, email me that, because empirical formula for triple or combined. I'll have to look on the spec. I can't remember off the top of my head. But anyway, I'll get back. I'll go through one practical, then I'll check the questions. Right. So yeah, there's different ways of measuring the energy, basically. You will need to know certain equations, which is beautiful. But if you're year 11, you don't have to learn them, but you still need to know your units, please. Most important. And also your escape method, equation, substitute, and then calculate. Okay, if you're not sure on that strategy, there's a video, or I can go over it again another time. It's not a problem. Oh, actually, no, I'll do that at the end. I'm just about to announce something then. Right, results. Yes, you do need to know that formula. So I've done a simple, I've done a simple diagram, can't think of the word then, of the setup. And what we have to remember, let me just check. Hang on, can I annotate? Yes, I can annotate. Oh, actually, no, hang on. Let me just stop that. I always forget that you can on this do. And yeah. Yeah, we'll go through the apparatus. You need something to measure the power and the energy. The heater heats up the block, so you have a little rod in there that sticks down the center, the middle of your 1 kilogram block. You always have another place for the thermometer, because you need to read the temperature. I've done this practical with just the block on the table. That raises issues, as it might, it will come up in there. What may they ask us about? So why do you need to insulate the block? Right, there are issues with this practical and things you need to be careful of. You're heating up the block. Now, if you don't have this insulation around it, we're going to use the word dissipates. That heat will go straight out and dissipate into the surrounding area. What you need to do is keep the heat in as best you can. Okay, so having the block insulated will make your data and your results far more accurate. Okay, so remember that word, that lovely word, dissipates. It's a beautiful word, I love it. Why is your answer not the true value? Because, well, it's never going to be, because there's always going to be heat escaping. Now, if you look around the block here, there's a gap. There's also a gap here. So heat can, even if you've got it all insulated, there's going to be heat release there. Your thermometer, there's a gap around your thermometer. What you can do or suggest is to add some water into these sections here, because the water will trap the heat that a little bit better. So it won't just be air. Heat will travel through air a lot quicker than water sort of thing. So it just keeps it more insulated. Okay, so you're never going to get a true value. So this is where this practical definitely needs improvement. Why is the temperature increase slower at first? like anything, you need time to warm up. Once you're there, it's all good. It's like with a car, with anything like a house, it takes so long to heat up, and then once it's at temperature, you can just like, oh, just keep it topped up. So yeah, it just takes a while because it's at the blocks to heat up. So yeah, if you imagine it, this heater here is heating up, and it has to actually get to the thermometer and then start warming up as well. Yeah. It may not be a block of metal. You could use a kettle to heat. Hang on, let me just move my bar out of the way. I can't actually see what it says. Thank you. And water in any other way of heating something. You could use a kettle to heat an amount of water or any other way of heating something. Okay, yes, you don't have to have a block. It's a specific heat capacity. Every single material will have a specific heat capacity. So you've got to, in the required practical, we use metal blocks, but yeah, it could be water has it, and everything has it. So you adapt the method to the material, basically. What's the resolution of temperature measurements? Resolution is your detail, basically. A thermometer will have to 1 decimal place. You could use to increase your accuracy. You can use a data logger or temperature electronic thermometer. That might be to 2 decimal places. You could, repeat it. Definitely repeat it, because an average is better than a one-off. And they could ask about repeatability and ask you to calculate the mean or the uncertainty. Okay, uncertainty, I've never really seen the uncertainty, really. So, but anyway, mean is just the average. Okay. But that is generally it. As I said, the main questions always asked is, how can we keep the heat in? What can go wrong? And also, it's all to do with the calculations. Hang on. To use it. No, that's what I was saying. Sorry, I was answering this question. It's not necessary to use a joule meter, as it says on there. And I think I remember from the video, I think they used a voltmeter and an ammeter. Oh, oh no, oh, hang on. Why is it not working? Sorry, I'm just making sure. So you can use an ammeter and voltmeter to work out the power. So the current times your potential difference will give you the power, and that's and then you can work out power, or you can work out the energy from them calculating power times by time, so however long it took. Okay, so there's different ways. I've never used a joule meter. I always had to use an ammeter and voltmeter on this practical. Okay. I think that was good for that one. So that's your first practical little things to remember. The second one, I'm hoping people watched my free electricity session on Monday, and I went through these practicals as well. Investigating resistance. What is the point of the practical? Oh, okay, resistance. How? Now I moved the bar. Now I can't read what's there. Well, I'll stick it there now. Actually, I could actually put it all the way down. All the way down there. Right. How difficult is it for current to flow through part of the circuit? Remember my analogy for electricity, resistance is going from, with the M25 4 lanes, restricting those lanes, but still having the same current going through, like the number of trucks and cars going through. If that's the case, they're going to slow down because they're going to get blocked up, basically. So that is what resistance is. With this, we're looking at the effect of the resistance as you increase the length of your wire. So you're basically calculating resistance of, well, it should increase as your length of wire increases, because you're just going a further distance, basically. There's more things to... Stella, it's just Jacob clearing up your cushion that you've ripped apart. Okay, sorry about that. I'm going to go back to bed now. Go sleep. Thank you. Anyway, sorry about that. She's actually gone to bed. It's too early to go to bed, Stella. Anyway. Right, bows. Long. So yeah, the further a car has to, or a truck has to go, or electron, the more it's going to hit and collide things, therefore creating resistance. So that's the theory, that the further it goes, the more collisions there are and the more resistance. The longer the wire, that's it, the thicker the wire. So the thicker the wire, there should be less resistance because you're opening up more lanes, you've still got the same amount of traffic. So it's like a nice, easy road ahead. Temperature. Temperature is like road rage, basically. Every time an electron hits a particle, there's going to be friction, there's going to be heat. How that relates to my truck and bread and motorway thing is the more resistance there is, the slower the traffic will be, and the more road rage you get. And you get really hot and bothered and start getting very cross with other people. No, I would never do that. It would never, ever happen in my car. Anyway, so they're the things you've got to remember for the results, okay? With this practical here, they often ask about the temperature. How can we limit the temperature? So we, as I said, the higher the temperature, the more resistance. So we want to eliminate that. Every time you do a reading, it has to go back to the normal temperature. So you have to pause and switch it all off in between your readings, okay? Because the temperature will affect the resistance. So make sure you switch it off in between, let it cool down for a few seconds, and then switch, move the crocodile clip along, and then switch it on again, and then measure the volts and the amps. And from that, you can, with the equation here, measure the resistance. Why must the power plant be kept on low potential? So low potential difference is your low energy, low oomph. So you're not forcing the traffic through or down the road. You're just making it nice and gentle, and therefore reducing the amount of collisions and heat, basically. Done that. Why is it important to switch it in between that? Is make the temperature go down. So you've got to make there's zero error. So make sure that that your readers or your equipment is all at 0 before starting. Resolution of measurements, that's all your decimal places and how accurate it is to read. Reproducibility, repeatability. Control variables, I say your control variables will be, on this one, everything's got to stay the same. It will be using the same wires each time, same distance as well. Yeah, not many control variables, really. It's pretty straightforward with this one. Hang on, let me just go to the chat. Yeah, it's, the electricity session is in your live session folder. Okay, so that's all there for you. Okay. But yeah, this is one of my favourite practicals. I really like it because it actually works. And you can see the difference in the resistance with the thicker and the thinner wire, and you can see as the wire gets longer on the x-axis that the resistance goes up and everything. And it's really nice and easy practical to do. And don't put your thumb on the wire because you might get a little bit of an electric shock. Anyway, not that I've tried it. The second one is a little bit more complicated. So this is looking at electrical components and how resistance changes through them. And it's all, again, you have to have a voltmeter and an ammeter. You need to definitely be able to draw a circuit with this. Please remember that the ammeter, which is basically your speed camera, goes in series. Your voltmeter goes across. If my head was the component, it goes either side of that component. It doesn't go in series, as you can see here. Let's make sure I come right. Yeah. So this thing here is going to be changed each time. So this one's a resistor, or it could be a bulb, or it could be a diode. I'm not drawing a diode. It's too complicated to draw a diode. I'm just being lazy, but yeah. So this bit here was what changes your component, that changes on that circuit. Okay, you're going to have a variable resistor. It helps to keep it all the same. So definitely know how to draw a circuit. Very important. And the other important thing that always crops up in questions is recognizing or drawing your 1, 2, 3 graphs, what a resistor looks like, lamp, and a diode. Okay, and what I've done here, I've added a website link as well to help with the explanation. So if you're not sure from this video, you can have a little look on that as well. And then from that, I can guarantee why. Why does it curve around? Why does that go up like that? Why does it do that? So it is really important to remember that when you're describing it, you must go, as the potential difference increases, which is your volts, as your volts increase, what happens to the current? Okay, and with your resistor, so this is your ohmic resistor, so it's your fixed resistor. What that's doing is always limiting the amount of traffic, is keeping it the same. Okay, so even if you increase your potential difference, which is your put your foot down, your energy, the resistor counteracts that and just keeps the flow of traffic going at the same speed, basically. So that's your current. So no matter how much potential difference you oh no, it doesn't keep it the same, it will keep it in relation, all the traffic in relation to the potential difference. So as you increase the potential difference, you'll increase the current in proportion, basically. All right, with the lamp, it is slightly different. So as you increase your potential difference in a lamp, what's going to happen is, like with the resistor, it will go up nicely, but then it will start to, the resistance will actually, or the current will start to slow down. So here it slows, because you can see that with the curve there. So less current is going through. They want to know why. And it's all because of heat and collisions between the electrons and the particles. Your particles, because you're putting more potential difference in there, you put more energy, particles are moving around, more collisions, more heat, that increases the vibrations more, and you just increase more and more collisions. Every time something collides, that's friction, that's heat. So heat increases, and therefore it slows everything down, basically. Okay, watch my video if you want another sort of explanation of the particles. That explains it. But yeah, with this, as in potential difference increases, current will also increase, but then in doing so, more collisions. So it will end up slowing the current down because there's more heat as well produced, which also causes more collisions. With a diode, so remember a diode will only allow traffic one way, so it's limiting which way the traffic is going. So if you are going clockwise around the M25, that's my electricity analogy there, you can't go anti-clockwise. So basically it won't allow it to go one way, so therefore even if you increase the potential difference, the road is blocked, there's nothing can go by, so that's why the current is 0. And then when you switch around and they change direction and go the other way, what your explanation is a little delay there as traffic starts to slowly get moving, and then all of a sudden it goes vroom, like that. So it's like when you've been in a traffic jam and all of a sudden it's clear up ahead, and it just takes time to clear, and then it goes, and then you can move quite fast. Maybe that's just me. Anyway, so that's what's happening with the diode. It's all because it's one way, blocked one way, can go the other way, done. So yes, they will mainly explain the pattern of each component. Okay. So I'll keep on about resolution and measurements and repeatability. That's just normal stuff. I think they're just filling in that bit. What have they got up here underneath me? Yeah, just know what the different components would do. Potential difference, the energy transferred to part of a circuit by each coulomb of charge. Resistor limits the current in a circuit. Yeah, so there's a few little definitions there. Yes, I think that's basically it. But yeah, obviously so many students just don't know the circuit, don't know how to draw the circuit, and then don't know the graphs. That's my main bit for this video on this practical. Okay. Right, I've included this one. It's not really which will require practical, but it's something to look at the resistors in series and parallel. What is the point? To find out what happens in total resistance when resistors are put in series and parallel. So again, if you watch my electricity one, it's all about traffic. So when you've got a series circuit, your traffic or electrons have only got one route, basically. And there's two snarl ups. It could be late or roadworks, it could be a car crash. So the car's got nowhere else to go. It's like a resistance, it's like a delay, basically. So with this, you just, you know, if you're leaving home and going to your mum's to visit or whatever, that's what I would do. I would probably hit on the A12 two lots of traffic, and that will slow me down. So I've got to add up that amount of traffic and those delays. So that's what you do for series circuit. But with a parallel circuit, it just gives the electrons or the trucks an alternative route. Okay, and in doing so, although, you know, they've all left, but like half of them might go one way, half of them might go the other way. So therefore you're reducing the amount of traffic, so you're cutting the current down, and they're only going through one resistor. Okay, so the resistance there won't be as bad as if 100% of the traffic went through it. So with a parallel, what you'll find is that, what's it actually saying here? Yeah, your total resistance will be less than the smallest resistance there. Okay, just because there's not much traffic going both ways. Okay. Can't increase the total resistance. The total resistance is less than the smallest resistor. That's for parallel. Yeah, each time you add more resistors, the current increases. More resistors, the current increases and the total resistance decreases. Well, let me get that right. Each time you add more resistors, more traffic jams, the current increases. Yeah, because you're slowing it down, so there's more there, and the total resistance decreases. There are more routes overall for the current. I'm not quite sure on that sentence there. I might have to double check on that one. But the most important bit is the total resistance is less than the smallest resistor. That is the important bit. That I'm going to have to double check on that. What may they be? What may they ask us about? Why aren't your results completely accurate? Yeah, that's down to equipment. If your machinery isn't correct, yeah, it could be faulty equipment. Your what is the resolution of measurements? Hopefully, yeah, to 2 decimal places. Current or potential difference. Yeah, so you need to know your equation for resistance, rearranging it, things like that. It's nice. As I said, I've just thrown this in last minute, but it's not one that's often asked. I love this one as well. This is brilliant. This one, density. So nice and straightforward, which we love. Love doing this practical. So density, so this is in your matter topic. Maths is involved, but it is like Key Stage 3 maths, so it's not too bad. What you've got to remember is, well, be careful with the questions is if they might ask, what's the density of a regular or an irregular object? So a regular object, hang on, am I allowed to draw? Yep. Regular, oh, maybe not allowed to draw. That's silly, isn't it? Right, hold on. Pen, thank you. A regular object is something like a cube where you can measure all the sides. So for this, you'll need to work out the volume. So that's your height times width times depth. But an irregular object could be something like that, or I don't know, anything really, a shell, a stone, something you can't actually measure. So with that, well, let's just break this down. To work out density, you need to know the equation. It's not on here. No, it's on the, oh my goodness. For both a regular and irregular, right, density equals mass over volume. Mass for both of them is to use a scale. That's all you need. Finding the mass, done. Okay. Volume for a regular equals width times height times depth. That's fine. and irregular, you need to use a Eureka can. And you don't even need to use a Eureka can. You can actually just use a measuring cylinder as well. But they'll probably want a Eureka can. And there's things you've got to remember with this. So you've got to fill it up until it stops dripping. So you have a little beaker underneath there, fill it up, and when it stops dripping, that means it's at the right level for the water. And then what you do, let's just erase that. Then you put the measuring cylinder underneath it, and you place your object, like I've done here, on a piece of string, and you dangle it so it is just under the water here, so that then the level of the water will obviously go up, and it will pour down there, and you will have your volume of your in this case, oh, actually, it looks like an egg. Anyway, you have a volume there. Now, this thing that they might ask is, don't put your finger under the water, because that will measure the volume of your finger as well. Okay, so you've got to be really careful where how carefully you put that object into the Eureka can. Balance, resolution, yeah, that's fine. You can do, yeah, it's 2 decimal places, that's all fine. How can you can, oh yeah, dropping it too quickly, splashing, you're losing water, you're losing your volumes. How can you get errors when weighing an object? Balance is not set to 0. You've got to make sure that is the case. What is the uncertainty of the measurements? The balance has a plus or minus 0.05 uncertainty. Here, as it goes, only goes up in 0.1. So, oh yes, it was divided by 2. Your uncertainty, it's your resolution divided by 2. So that's where is it on your uncertainty? So whatever your uncertainty is, if they ask for that, it's your resolution. So that is your marks on the measuring cylinder. It might be like 0.1 centimetre cubed divided by 2, and that tells you the uncertainty. So it's like kind of halfway between a whole band. But anyway, there's a site on BBC Bite-Size if you need to know a bit about that and we're calculating uncertainty, probably more for separates than combined. Really straightforward practical. Again, if you get asked to write out the method, don't forget you can do bullet points. Make sure you write it so that someone can pick it up and reproduce it themselves. And don't forget to put all the calculations in. Okay, so that's it for combined. We are now doing the separates one, which is your thermal insulation. So there's 2 parts of this. Investigate the effectiveness of different materials as thermal insulators, and the different thicknesses of thermal insulators. I've just done it as one, but anyway, I've just added 2. And what I've done here, I've added a method just to show you, and some lovely little diagrams here. Let me just move myself over there. So this one is probably more like your control here with no insulator around it. And here, if you've got a beaker within a beaker, you can add a little bit of insulation around there. It could be cotton wool, could be cardboard, whatever else they put. They give you cloth, that sort of thing. Okay, so you're measuring how quickly things cool down, basically. So you need to specify maybe need to specify a time scale when you're describing how often you need to check the temperature. Yeah, every 3 minutes or 15 minutes perhaps. So you need a sort of significant amount of time. Always make sure this is your control variable, that you've got the same volume of water in there. Try and start the temperature around the same temperature, basically. The lid is very important. Again, don't forget, it's all about energy. Like with the specific heat capacity, it's all about the dissipation of heat out. So if you've got the lid, it will just stop the dissipation of heat energy out, keeps it in, and makes it a far more accurate answer. It's not, again, it's a really nice little simple practical. Really like it. And they'll, yeah, 9 times out of 10 they'll ask you to plot the cooling temperature. So don't forget, your X is your independent variable, your Y is your dependent variable. So what you're measuring is your temperature, and then what you're changing is actually with this one here, you've got your different material. So this will be time over time, and yeah, temperature and time. And then you've got your different materials here, and make sure you add a key if you're doing that. Really important. Also, they might explain what's happening. What is heat? It's all about conduction. Make sure you know about conduction, convection, and radiation as well. That could be included in the questions, like what type of thermal movement is this, that sort of thing. So remember, conduction is to do with solids, convection is gas and liquid, radiation is just your waves. Okay. Yeah. What may they ask us about? He will always be transferred. Oh yeah, that is important to remember. Heat will always travel from hot to cold until it gets to equilibrium. How can this experiment reduce unwanted energy transfers? That's what I was saying about the lid. Thermal conductivity of an object. Right. Oh yeah, a higher thermal conductivity means that it's faster rate of energy transfer. Make sure you understand that. There's questions like talking about thermal conductivity. So heat, how heat can conduct in that. So higher means it can travel faster through it. So if it's going from here from A to B, it'll be really quick if it's got high thermal conductivity. If it's got low thermal conductivity, it's more like an insulator. Okay. So what you're looking for is a material that has low thermal conductivity to make sure it keeps the heat in. How to improve accuracy? Definitely with a digital thermometer, just like what we're doing with specific heat capacity and other practicals. It's always better with a digital thermometer, far more accurate. But yeah, some really nice practicals. I really like them. I know I moan about physics, but actually these practicals are not too bad. I really like them. They're nice and simple. And yeah, I can't complain. Wait till paper 2 though. I will complain. No, I won't really. No, actually I will complain. I don't really. Hang on. I'm going to keep that. But that's your required practicals for paper 1. Okay. Right. Exciting news. I know what I'm going to do next week. And that is, it comes from talking to quite a few of your students. But what I'm going to do, I'm going to get a biology, a chemistry, and a physics 6 marker. And I'm going to talk through how to answer them. I think a lot of you need to be shown how simple 6 markers are, because a lot of you ignore them and they're getting hurt feelings. So we need to tackle 6 markers. So I am actually going to do a walkthrough, talk through 3 horrible 6 markers. No, they're not going to be horrible, because I'm going to show you how actually with a specific strategy you will be able to answer them, or at least try and attempt them. Okay, so that's what we're going to do next week. Okay, so I will be emailing around, and what I might do is email around, try maybe email the questions first. I think maybe you can all have a little go, and then I'll go through and answer them for you. Okay, so that's the thing. Also, is there any more? Are there any questions from today, or have you got any other ideas that I can cover in these sessions at the moment? If you can't do anything now, then we can do. Hang on, let me just go. Need to go through. Oh, hang on. What year are you, Elliot? Because I can't remember. You year 10? Oh, you are little. Oh, okay, good. We have coming up in April and May, we have past, well, there's going to be 2 months of past papers basically. But what I'm also organising at the moment is 10 weeks of going through exam questions, talking through exam questions after Christmas. And that is with 2 other teachers. So I'll be doing the biology ones, and I've got a chemistry specialist who's an examiner as well, and a physics specialist, and they will be going through each week. They'll go through a different module, and we're going to pick out exam questions, and you guys are going to sit in, listen, and learn how to answer exam questions. And we're going to try and pick some really critical questions that often come up, and so just to teach you really how to answer them. Okay, so that is after Christmas. Okay, we are still planning it, so you're more than welcome to join whatever module you want to do, and they will be recorded and you'll be able to have them. But we're also sort of advertising and selling the course as well, so if you've got your friends that are interested in that, then please share. But for you guys, I will, at the moment, yeah, I will let you join in for free. I'll have to make sure it's okay with the other 2, obviously. But is that okay? That is coming. We're you know, because we think it's really important to go through exam questions. So it is on the to-do list. Okay, and it will be available after Christmas, ready for April, May, and June. My goodness. Okay, is that okay, Elliot? It's all good. Got everything taken care of. Right, I will stop the recording there.